All right, let's dive right in. We're going to open the box on one of the most famous and, honestly, one of the weirdest ideas in all of science, Schrödinger's cat. You've heard the name, right? It's this thought experiment that's been bending minds for almost 100 years. So let's figure this thing out.
So, let's start with what everyone kind of knows. You've probably seen the picture or at least heard the phrase, right? This cat stuck in a box with its life literally hanging by a thread. Or, well, by the random whim of a single tiny atom. It's become this super iconic symbol for quantum physics. But man, is it misunderstood.
And this whole setup forces us to ask a really weird question. Can a cat, or anything for that matter, really be both alive and dead at the exact same time? I mean, your gut reaction is probably, no way, that's impossible. And guess what? That feeling, that sense of absurdity, that is exactly the point.
Okay, so, first things first, and this is super important. This was never a real experiment. No cats were ever harmed in the making of this paradox, I promise. Back in 1935, a physicist named Erwin Schrödinger dreamed this whole thing up as a thought experiment. Basically, it was a story he made up to show just how ridiculous the rules of quantum mechanics can sound when you try to apply them to our normal, everyday world.
So here's how it works. Picture a steel box, totally sealed off from the world. Inside we put a cat. Along with the cat, there's this little contraption with a single radioactive atom. Now this atom is a ticking time bomb, but a random one. It has a 50-50 chance of decaying within an hour. If it does decay, it triggers a hammer, the hammer smashes a little bottle of poison, and, well, you know. The key thing here is that the cat's entire fate is now tied to the completely random quantum state of this one tiny particle.
And this is where things get really weird. According to the bizarre rules of quantum mechanics, until we open that box and look, the atom isn't either decayed or not decayed. It's in something called a superposition, which is a fancy way of saying it's in both states at the same time. And because the cat's fate is tied to the atom, the theory says the cat is also in a superposition. It's simultaneously alive and dead. Yeah, I know. Just let that sink in for a second.
But hold on, because here's the big twist in the story. Most people think Schrödinger came up with this to explain all that quantum weirdness. But that's not it at all. It's actually the opposite. So let's pull back the curtain and find out what he was really up to.
And this quote right here, from the man himself, is the smoking gun. He literally called his own idea a ridiculous case. So you see, he wasn't celebrating some cool new discovery about quantum mechanics. No, he was setting the stage for a major complaint. Yeah, let's just be super clear about this. This whole cat in a box thing, it wasn't an explanation. It was a complaint. It was Schrödinger basically throwing up his hands and challenging his colleagues, saying, look at the absurd place your theory leads.
So let's break his argument down. He just found it completely insane to think you could take these fuzzy, maybe this, maybe that rules from the tiny quantum world and apply them to something big and solid like a cat. He was basically saying to the other physicists, hey, if your theory is right, then this zombie cat has to be possible. And since that's obviously ridiculous, doesn't that mean your theory is missing something? Okay, so to really get why he was so annoyed, we have to take a quick look at the one quantum rule that started this whole mess.
And it all boils down to this one idea, superposition. The best way to think about it is like this. In our world, things have to choose. A light is on or it's off. But at the quantum level, a particle can be lazy. It doesn't have to choose. It can just exist as like a cloud of all its possible states at once. So our atom isn't just waiting to decay or not decay, it's doing both. And it's only when we peak, when we measure it, that this cloud suddenly collapses and snaps into one single reality.
And that right there is the fundamental conflict. Our world, the world we see, is an or world. A coin is heads or tails, a car is here or there. But the quantum world is an and world. A particle can be in state A and state B. And showing just how crazy that clash is, well, that was the entire point of Schrödinger's cat.
So what's the magic ingredient that breaks this quantum spell? It's us. It's observation. The simple act of looking at something, of measuring it, forces that particle to stop messing around and pick a side. Physicists have a cool name for it, wave function collapse. The moment we crack open that box, that whole both states at once thing just shatters, and the cat is suddenly and definitively one or the other, alive or dead.
And this whole thing just perfectly highlights three of the biggest, deepest headaches in all of physics. First, you've got the measurement problem. I mean, when exactly does the universe make its choice?
When the atom decays, when the poison vial breaks, or only when we, the human, open the box. Then there's the observer problem. Does reality actually wait for us to look at it before it becomes real? And finally, the boundary problem. Where's the line between the quantum world and our world? At what point does an object get too big to be in two places at once?
So, okay, fast forward to today. Almost 100 years later, have we figured this thing out? How have scientists tried to solve the puzzle that Schrödinger laid out so perfectly? Well, let's take a look at the leading theories.
All right, so there are a few big ideas competing here. The old school one, the Copenhagen interpretation, pretty much says, yep, it's weird, but the cat really is in both states until we look, and our looking forces a result. Then you have the super sci-fi idea, the many worlds interpretation. This one says both things happen. The universe literally splits into two. In one universe, the cat's fine, in the other, it's not. We just happen to find ourselves on one of those branches. And then there's the more modern idea, decoherence.
Now, decoherence is where a lot of physicists are putting their money these days. And the idea is actually pretty intuitive. It argues that something as big and complex as a cat can never be truly isolated from its environment. Think of the superposition as a secret. A single, tiny particle can keep a secret really well. But a cat? It's interacting with millions of air molecules, the box walls, heat, all of it. Each one of those little interactions is like a tiny measurement, peeking at the secret. So the secret of the superposition gets leaked out into the environment almost instantly. In this view, the cat was never really in both states at once for any meaningful amount of time. Reality chose a side long before we ever got there.
Okay, so if an idea like decoherence kind of solves the paradox, why are we still talking about this cat almost a century later? I mean, what's the big deal? Well, it turns out its legacy is way bigger than just Schrödinger's original complaint.
It's kind of funny, actually. The thing Schrödinger invented to show how absurd quantum mechanics was has become one of the best tools we have to explain it. The very ideas he hated are now the groundwork for some seriously revolutionary tech and some of the biggest philosophical questions out there. We're talking everything from quantum computing all the way to theories about parallel universes. And this is where it stops being a thought experiment and becomes real world-changing technology. A quantum computer, it basically runs on the same weirdness Schrödinger was complaining about. The basic units inside it are called qubits, and you can think of each one as a tiny, perfectly controlled Schrödinger's cat. Because they can be a 0 and a 1 at the same time, they can chew through calculations that would take a normal computer billions of years. It's unlocking the power of the AND world.
So we kind of end up right back where we started, with this huge, mind-bending question. Because even if a theory like decoherence solves the problem of the cat, it doesn't solve the deeper mystery. This whole thought experiment forces us to think about our place in the universe as observers. It really makes you wonder, if the universe, at its most basic level, is just this fuzzy cloud of possibilities, what does it even mean for something to be real? And what does it say about us that the simple act of looking might be part of the answer?